how do you remove an outlier from linear regression? I know this is last week's or last lesson, but the literature and the lecture and the video, it says, you know, sometimes you'll have an outlier that needs to be, if you remove it, how do you actually remove it?
You just delete it. Like you just physically go into the spreadsheet and hit delete.
Seriously, that's all you do?
Yeah, that's it.
Okay. Thanks.
No problem. All right, I'm working on, oh, there it goes. Okay, now can you guys all see that? And, all right, so first let's just talk a little bit about the exam itself. There's 44 total questions and you have your usual 4-hour time limit, but like the other exams, I don't expect it to take 4 hours for anybody. This one does have a few more questions than normal, like only a handful though, so it might take you slightly longer than the other exams, but it really isn't that much longer than the other exams. It is worth a little bit more than the other exams though. It makes up a slightly higher percentage of your final grade, so it does carry a lot of weight. The exam itself is cumulative like all of our exams, but I would say this one is even, well, I mean, we're at the end of the semester, so now, you know, we have so much stuff that we know. So I would say it's about 50% new material, meaning like the correlation and regression that we've just recently talked about, and then 50% of old stuff from the whole semester long. What I recommend is making sure that you look at all the review materials that we've had in the past. So looking at the past test reviews, those were like the group quizzes that you guys did that were test reviews. So for lessons, that was lessons 8, 15, and 20. And then if you have time to watch the past test review videos, like this one that we're doing now, then that would be definitely helpful also. And so now that we're at this point in the semester, we have like this giant toolbox full of statistical tools that we can use to analyze data with. So this is kind of a list of all the different statistical methods that you guys have learned how to do over the course of the semester. So we have looking at one mean with sigma known, one mean with sigma unknown, paired data test, independent samples test, looking at one proportion, the difference of two proportions, chi-square test, ANOVA, and now we finally have linear regression to add to that toolbox. So the first part of the exam is going to be, I think there's 6 questions where it just gives you a scenario and you have to choose which of these different methods that you should use to analyze it. And now there's lots to choose from because we have so many that we know about. And for each of these methods, even beyond the first 6 questions of the test, you need to know all the nitty-gritty details. So you need to know how to write the hypotheses for a particular test. You need to know the requirements, keeping in mind that the requirements do change depending on which test or confidence interval that you're trying to do. You need to know how to actually conduct or carry out or calculate the test or the confidence interval. Of course, you're going to have Excel, so you can use Excel to do any of the heavy calculations. And then you need to know how to write the conclusions. And really, the conclusions part, if you've kind of mastered that one over the course of the semester, then it's more of the same, you know, picking out conclusions from a list of a whole bunch of different conclusions. So, so here's some examples that we're going to go through to see if we can figure out which method we should use. So these are similar to what you're going to see in the first part of the exam. So the first one says, a major study of alternative welfare programs randomly assigned women on welfare to one of 2 programs called WIN and Options. WIN was the existing program. The new Options program gave more incentives to work. An important question was how much more, on average, the women in Options earned than those in WIN. So why don't we first, well, it's hard to like really give like a broad thing, but I still kind of look and say, okay, well, what am I measuring here? And what am I comparing here? So I look at the response variable, which is what I measured. So in this case, we're measuring how much people made. So, because we're looking at, we wanted to know how much more people earn. So we're looking at earnings. So is earnings categorical or quantitative? So if you want, we can just do, you know, hand symbols. So C for categorical, and what did we do for Q? Something like that. Oh, we did this. This is sign language Q. All right. No, upside down. Or, okay, do something that doesn't look like a C, and then we'll know you're talking about a Q. So do you think this is categorical or quantitative? Yes, quantitative, because we're talking about how much we earn. Exactly. So then I look at, okay, are we comparing different groups? And in this case, we are comparing different groups. How many different groups are we comparing? 2. Perfect. So we have 2 groups for a quantitative variable. So then we just have to decide, okay, well, then are these 2 groups independent or dependent? So if they're independent, then they're, you know, they were assigned randomly which group they're going to be in. There's no logical link between a woman assigned to the win group and a woman assigned to the options group. Knowing who's in the win group doesn't tell you who's in the options group, things like that. If it's dependent, then there was some kind of matching or pairing going on here. So in this case, let's see, did we have a hand symbol for independent and dependent? I can't remember. Okay, that looks good. So I for independent, and if it's dependent, then do a D. So perfect. I. So this one is independent because the women, they just took a whole bunch of women and they randomly assigned them to the 2 groups. So there's no logical pairing with a woman from the win group and a woman from the options group. So after all that deliberation, we end up with the 2 sample independent procedures that we would use. 2 means, I should say, maybe. 2 means independent. Okay, that wasn't, there we go. All right, next one. A survey of students in 8 Arizona schools wish to determine if the smoking habits of students, 2 categories, student smokes or student does not smoke, was related to their parents smoking. 3 categories, parents smoke, 1 parent smokes, or neither parent smokes. All right, so this one, are we talking categorical or quantitative? Yep, categorical. So we have categorical variables, and this one's a little bit different as far as we're deciding 1 group, 2 groups. We have 2 variables that we're looking at. Sorry, somebody in my street has like their alarm went off or something. So the massive car honking, it's not mine, I promise. So the first variable, smoking habits of students, has 2 levels, 2 categories, and the second one has 3 categories. So if we have 2 categorical variables and at least one of those has 3 or more levels, then that would automatically make it a chi-square test. So another way to figure out if it's chi-square is kind of a little bit by the wording. So we wanted to find out if, you know, variable A was related to, or another way they usually like to word it actually is independent from their parents' smoking habits. So when we're looking at the relationship between 2 categorical variables or looking to see if they are independent, I think my whole street is honking. I think one car set off another one. Okay, I think I'm spelling independent wrong too. Is it E-N-T or A-N-T? Something about when you have to write in front of other people, then all of a sudden, like any spelling skills that I ever had, like go out the window. So if they use the word independent in relation to 2 categorical variables, then that's another indication that we would have a chi-square type of situation. Okay, next one. The ARSMA, Acculturation Rating Scale for Mexican Americans test, was compared with a similar test, the Bicultural Inventory, by administering both tests to 22 Mexican Americans. Researchers wanted to know whether the population mean scores for the 2 tests are the same. So first we look at categorical versus quantitative. So say we have categorical variable or quantitative. It looks like what we're measuring is score on the test. So yeah, so that's quantitative. And another clue here is we're talking about a mean, so we have keywords there. So we're looking at quantitative, and are we comparing one group, two groups, three or more groups? Two. So we have the ARSMA test and the BI test. So then we just have to decide whether the samples are independent or dependent. So yeah, so this one would be dependent because both tests were given to the 22 subjects. So all the subjects took both exams, and then they compared those scores. So knowing who took the ARSMA test tells you exactly who took the BI test because it was the same people. So this time we're going to have two means or two samples, or we could just call it paired. I'll call it that. Paired test. All right, because elderly people may have difficulty standing to have their heights measured, a study was done to see if height to the knee could be used to estimate a person's overall height. So this one is a little bit different. You know, if you sit down with your standard, hey, are we measuring categorical or quantitative? You'd probably come up with quantitative, but then you'd realize that they were actually measuring two things here. So they're measuring a person's overall height, and they're looking at the person's height to the knee. So we have two quantitative variables that we're looking at. So when we have two quantitative variables that we're looking at, that's going to lead us to regression, the kind of the latest tool that we've learned how to do. So one way to tell that it's regression is, you know, that it has those two quantitative variables. Also, usually one of our goals for regression is to make predictions or to be able to estimate things. So here it says that we did this study to see if, you know, variable 1 could be used to estimate variable 2. So that's kind of another indication that we would be dealing with regression. All right, suppose there are 3 routes you can take to work and you're interested in determining which is the fastest. Each day you randomly choose a route to take and measure the time it takes you to get there. After 30 days, then you analyze the data. All right, so in this case, we are measuring the time it takes to get to work. So is that categorical or quantitative? Yep, quantitative. So quantitative, and then we have to look at how many things are we comparing, how many groups are we comparing. And it says we're looking at 3 routes, so we are comparing 3 groups. So if we have a quantitative variable comparing 3 or more things, then the correct one is ANOVA. I feel like ANOVA and chi-squared, those are kind of the easier ones to pick out because they're a little bit different in the way that they're worded. All right, when a police officer responds to a call for help in a case of spousal abuse, what should the officer do? A randomized controlled experiment in Charlotte, North Carolina studied 3 police responses to spousal abuse. Advise and possibly separate the couple, issue a citation to the offender, and arrest the offender. The effectiveness of the 3 responses was determined by whether or not the subject was rearrested. All right, so here we're looking at 2 variables. Again, this time the variables are both categorical because we're looking at the response to spousal abuse, and there was 3 options for that. And then we're looking at the effectiveness of the response based on whether or not the subject was rearrested. So whether or not a subject is rearrested, that's like a yes/no kind of thing. So that one's also going to be categorical. So when we are looking at 2 categorical variables and trying to see if there's a relationship or if one is independent of the other, then the appropriate analysis would be chi-square. All right, next one. A noted psychic was tested for ESP. The psychic was presented with 200 cards face down and asked to determine if the card was one of 5 symbols: a star, a cross, a circle, a square, or 3 wavy lines. The psychic was correct in 50 cases. You wish to see if there's evidence that the psychic is doing better than just guessing. That is, if the percentage of correct guesses is better than 1/5 or 20%. All right, so this time we're measuring whether or not the psychic was correct. So is that going to be categorical or quantitative? Perfect, categorical. So we have a categorical variable, so we have to decide if we're looking at one proportion or two proportions, or three or more proportions. One or two, what do you guys think? Okay, good guess. One. So basically we just had one sample here. We had the one psychic and they got the 200 cards and they measured how many times they were correct. So we just have one sample that we have and we're comparing that one sample value to a single number. So that makes this a one proportion. Sometimes I think that helps ones get a little bit tricky, I think, because you're thinking, oh, well, I'm comparing two proportions to each other because I'm comparing that 20% to the 25% that they got from the sample. But if you go back and say, okay, well, how many samples did I have? And here I just have one sample that I'm comparing to a single number. That's what makes it one proportion. So if I had two samples, then that would be what would make it two proportions. All right, so just some general ideas, and I feel like I've kind of talked about these in almost all the test reviews, but they're still good things to remember, and they still keep coming up on the exams over and over again, which is why I keep talking about them over and over again. So when you're writing the hypotheses, the null hypothesis always has the equal sign in it. So it would also technically be correct to say less than or equal to or greater than or equal to, but if you just remember that it always has the equal sign in it, then you'll be good, especially on these exams because they always just use a plain old equal sign for the null hypothesis. For the alternative hypothesis, you'll either have greater than, less than, or not equal to, and you have to read the problem to see what the context clues are to figure that one out. And actually, I feel like as a whole, like our class does a really great job with figuring out the hypotheses. I don't think people miss those very often. Now, some of the exceptions to writing the hypotheses are analysis of variance and chi-square. So those hypotheses are written a little bit differently. So for analysis of variance, the null hypothesis is that all the means are equal. It could also be written out as mu1 equals mu2 equals mu3 equals mu4, however many you have. And then the alternative is that at least one mean is different. And then for chi-square, for the null hypothesis, we have variable 1 and variable 2 are independent for our null hypothesis. And then the alternative is that they are not independent. So the key with ANOVA and chi-square is that just making sure that you get the wording right, because there's ways to say something similar that actually turns out to be not correct. So just make sure, just write down in your cheat sheet or something, the wording here, and look for the ones that are worded this specific way so that you don't go with a differently worded option that is actually incorrect. Sorry, dropped my pen. When we're writing conclusions for the hypothesis test, when P is low, then HO must go. So if the p-value is lower than the significance level alpha, that's when we reject the null hypothesis. So if we reject the null hypothesis, that means that we have sufficient evidence that the alternative is true. And if we fail to reject the null hypothesis, that means that there is insufficient evidence that the alternative is true. So the thing to note here is that either way, reject or fail to reject, it's always the alternative that is going to be talked about in the remaining part of the conclusion. And then just noting that reject goes along with sufficient evidence and fail to reject goes along with insufficient evidence. And my best advice for the problems where it asks you what the conclusion is to not even look at any of the options. I got to put my phone on silent too. Man, I'm having like a really bad noise in the background distraction day for this thing. So I'm really sorry. Apologize. I'm going to blame it on the snow. Again, I'm just going to blame everything on the snow today. All right, so my best advice is to just not look at any options that they give you and write out, like by hand, what you think the conclusion should be using this kind of formula here. And then once you have it all written down on your paper, look to see which one of the options that they give you matches the one on your paper. Because I feel like they give you a ton of options. Sometimes they give you up to 8 different options to choose from on these conclusions, and they purposely word them to try to confuse you. Like they tweak things just a little bit that makes them not right. You know, they'll switch out a sufficient for an insufficient, or they'll switch out the null hypothesis with the alternative hypothesis or something to make it slightly not wrong. So I feel like if you have it written in front of you and then you find the one that matches what you wrote down, you're much less likely to be swayed by some of the other options there that look, you know, that cause you to second guess yourself, basically. So if you write it out first, then there's no second guessing. You just find, hey, here's the one that matches exactly what I just wrote on my paper. Done. When we're writing conclusions for confidence intervals, these always mess people up a little bit. If we're just writing a conclusion, we're going to say we are, you know, whatever % confident that the true mean is between blank and blank, or that the true proportion is between blank and blank, or that the true difference in the means is between blank and blank. So words that you want to really watch out for are chance or probability, because if we have a concluding statement that has an actual confidence interval, like the actual numbers from a confidence interval in it, then you can't use the words chance or probability in, about that interval. The other thing you have to watch out for is statements about individuals or other sample means. So your confidence interval is always about the parameter, either the true mean, the true proportion, the true difference in the means. It's never about individual values or future sample means or things like that. And then if you got all that mastered, the one that sometimes still throws people off is sometimes they put in a statement like this. So confidence intervals are based on a method that produces confidence intervals that contain the true mean, you know, whatever % of the time. So it is correct to say that 95% of all 95% confidence intervals will contain the true mean. So that's kind of just that's based on the, like I said, it's based on the method that we use to construct the confidence interval. So that statement is correct. All right, so let's start talking about the new stuff that we've just covered, where we started looking at relationships between 2 quantitative variables. And we like to give the variables special names just so we can distinguish between which one we're talking about. So we call them the response variable and the explanatory variable. So the response variable, or the dependent variable is another name for it, is what you're trying to predict or estimate. So it's the output, it's the, you know, what kind of comes at the end of the line kind of thing. And then the explanatory variable, which is sometimes called the independent variable, is what you're using to make that prediction. So it's going to be your input. So explanatory is like the input, and the response is like the output. So here's some examples. We're going to see if we can identify which variable is the response variable and which variable is the explanatory variable. So here's the first one. The Columbus Zoo conducts a study to determine whether a household's income can be used to predict the amount of money the household will give to the zoo's annual fund drive. All right, so first thing, we just want to see like what are the things that we're measuring here. So we're looking at household income and the amount of money that the household will give to the zoo's annual fund drive. So those are the 2 variables. So we have to decide which one's going to be our X and which one's going to be our Y. So remember, the thing that we're trying to predict, our output, is going to be the Y. And the thing that we're using to predict is going to be your X. So in this case, the amount of money that the household will give, that's what we are trying to predict, so that's going to be our Y. And it says household income, can it be used to predict? So whatever we're using to predict, that's going to be our X. So household income would be the X, and the amount of money donated would be the Y. Does that make sense? All right, the second one, the height in feet and volume of usable lumber in cubic feet of 32 cherry trees are measured by a researcher. The goal is to determine if volume of usable lumber can be predicted from the height of the tree. So our two variables are volume of usable lumber, and the other one is height of the tree. All right, so do you think that volume of usable lumber, do you think that is the X or the Y? Guess you could make like X or Y, like YMCA. Okay, or Diana, you're so good at the whole, I forget all my sign language. You've got it mastered. Okay, so yes, the volume is going to be the Y, and the height is going to be the X, because we're trying to see if usable lumber can be predicted. So what we're trying to predict is the Y. From height of the tree, what we're using to predict is the X value. All right, so once we've got our two variables, the first thing that we always want to do with our data is graph it. Okay, graphing, it's going to give us a nice visual representation of the data. And in this case, because we're looking at these two quantitative variables, we want a visual representation of the relationship between X and Y. And the three things that we're kind of looking for on this scatter plot are form, direction, and strength. So form is it linear or is it non-linear? That was the kind of the fat hot dog shape that the book mentioned. Direction, positive or negative. If it's positive, then as X increases, Y also increases. And if it's negative, then as X increases, Y decreases. And then strength is just, okay, well, how fat is the hot dog, basically? I mean, are we talking about like a skinny little turkey dog, or are we talking about like a Costco hot dog, or do we have to put the bun on the hot dog? I mean, like the skinnier the hot dog, the stronger the relationship there. So once we, oh, I thought I had the scatter plot next. Oh no, I guess I've had that after. Once we look at the scatter plot, the next step is going to be to look at a numerical summary of that relationship. And we do that by looking at the correlation. So here's a few pieces of information about correlation. First of all, it measures the strength of the linear relationship between X and Y. So that's something that can be a little bit tricky for beginning statistics students, is that in statistics, when we talk about correlation, first of all, it only looks at linear relationships, so it has to be a straight line. If it was a rainbow shaped or something, it might be a relationship, but it's not described by correlation. And the other thing is that it's between two quantitative variables. So like in statistics, we don't talk about the correlation between like gender and income or something like that, because gender is not quantitative. So if you look at the formula for calculating R, correlation, like there's nowhere to put a categorical variable in there. So, so correlation measures the strength of the linear relationship between two quantitative variables, X and Y. Correlation, or R, can take values between -1 and +1. So the sign on the correlation indicates the direction, positive or negative. And then the value represents how strong that relationship is. So the closer you are to 1 or -1, the stronger the relationship, and the closer you are to 0, then the weaker the relationship. Oh, and one more thing is that correlation is really, really affected by outliers. So here are some different scatter plots, and at the top I have some different values for correlation, and we'll see if we can match the value for correlation to the scatter plot. So now I'm really going to test your sign language skills here. All right, so we'll start with the first one, the 0.030. So looking at the graphs, A, B, C, D, E, which one do you think would have a correlation of 0.03? All right, seeing some mixed answers. So 0.03 would go with D. Because this one is really, really close to 0. So when it's close to 0, that indicates like no linear relationship between X and Y, either positive or negative. So we're going to see just a giant, you know, kind of like back in my day when you turned on the TV too early in the morning and there was just like white snow on the TV. I don't think they have that anymore. I think things are on TV like all the time, but when I was a little kid, I remember like waiting up for the, you know, I'd get up early on Saturday mornings to watch cartoons and have to wait for the snow to go away. So D is going to be that 0.03. Okay, next one, the 0.915. So which of the remaining graphs do you think goes with 0.915? Awesome, C, absolutely, 0.915. So 0.915 would indicate a pretty strong linear relationship, positive linear relationship between X and Y. And that's what we're seeing here with graph C. So the next one, 0.735, and here you can kind of compare these two. So 0.735, you can probably guess is this one over here. And both of these are positive, as you can see, but one of them has, you know, this one's the turkey dog, and this one's the Costco, you know, Polish dog going on over there. So the closer that you are to 1, which this 0.915 is, then the stronger, the tighter that relationship is going to be. Okay, and kind of a similar thing going on with the remaining two that we have here. The difference with these two is that these are negative. So that just means that the direction of, like, essentially the slope is going the other direction. So which one do you think should be negative 0.544? A, perfect. And then of course that means that this last one should be negative 0.939. All right, so here's another question for you. Okay, of these 5 graphs with their corresponding correlations, which one, A, B, C, D, or E, has the strongest correlation? All right, so the correct answer is E. E has the strongest. Sometimes this can be a little bit tricky because I think sometimes people see the negative and they think weak. Remember, it's the closer you are to -1 or +1. The sign just indicates the direction. The value indicates the strength here. So we had a couple people that selected C as the strongest. This one is pretty strong, but if you compare that 0.915 with the 0.939, then the 0.939 wins out. So remember, when you're deciding on the strength of the relationship, you can kind of ignore the sign and just focus on the actual numerical value, because the sign just indicates direction. All right, so once you've done a scatter plot, you've found the correlation, then you're ready to model the data. And we do that with what we call a linear regression model. So this is what our model looks like. We have y hat is equal to b0 plus b1 times x. So y hat is just the predicted value for y. So anytime we put a hat on something in statistics, it's the predicted value for whatever that is. So like our p hat, when we talked about proportions, we were talking about estimated value for p. So anyway, y hat is our predicted value, it's our output. The b0 is the y-intercept. So it's the value that we would expect for y if x was equal to 0. And most of the time, it's not really, as far as a value, the y-intercept usually isn't going to be that interesting unless it would actually make sense for there to be values of x equaling 0. So, which doesn't happen most of the time. So like, for example, if we were looking at like a a model to use somebody's height to predict how much they weigh. Well, if height was X, like how many people do you know that are 0 inches high? Like not any. So, so the value, like the numerical value of the y-intercept, as to interpret that wouldn't really make sense because we don't know anybody who's 0 inches high. But the y-intercept does make the model work, so we still have the y-intercept in there, but it's not like our favorite part of the equation. Okay, so the favorite part of the equation is going to be the slope, okay, B1, because the slope is going to really quantify the relationship between x and y. So slope is a rate of change, and it's going to tell you for every 1 unit increase in x, we expect y to change by whatever the value of slope is. So if we were looking at height and weight, you know, it might say, okay, for every 1 inch increase in height, we expect your weight to go up by 6 pounds or something like that. So this one, we can interpret the actual value from the equation, and that interpretation is going to be interesting and meaningful for us all the time. And then, of course, x is just the explanatory variable. So you're going to plug in your x variable and then output your y hat value. So here's an example. Suppose we want to see if a person's height can be predicted from their arm span. And data is collected on 25 college students. So the height is measured from head to foot, and the arm span was measured from fingertip to fingertip across the back shoulder blades. So in Excel, we can have Excel do all the different analyses for us, which is pretty great. So the first thing we want to do is graph it. We want to construct a scatter plot. So first thing you need to do in Excel is you need to enter in the data in where it says explanatory variable and response variable. So just making sure you have the right variable in the right column and pasting those in there. And when you do that, then over here, it should create a lovely scatter plot for you. Now, sometimes, like when I did this particular one, then it wanted to start my x-axis on 0 instead of 50, so I had a whole clump of data over in the corner. And if you just double click on the axis, then it will let you change those values. So I just went in and manually told it, hey, I want the axes to start at 50, not at 0. So you might have to mess around with it just a little bit in Excel to make it be a nice looking graph. So if you have your graph, here's the same graph again. Then again, we're looking
to change that.
Where do you go? So here, let me show you. Okay, so this might be kind of a mess. I'll move this one out of the way.
Oh.
Whoops. Now I don't know how to, I lost my scroll bar. Come back. Maybe if I arrow over, we'll go that way. There we go. Okay, so what I did to change it, so this is after change.
I think I'm gonna.
Your sound is not working.
If you just double, oh, my sound's not working? Can you hear me now?
Start it again.
I can hear you now.
All right, sorry. Okay, so all I did was, here, I'll get back out of there again. So this is kind of what it looked like when I first did it. And so what I did is I just double clicked on this bottom axis. And when you double click on that, then Excel brings up some different options that you can do. And you might have to click along here to find the right one. But I'm looking for the one that says bounds. And right now it's automatically choosing 0 to be my lower bound. And that's lame because it's making my graph be not that pretty. So I just looked at my data and I said, okay, well, if I start at 50, I think that might be pretty good. So I just changed that to 50 in there. And then it made my graph look better. So I fixed it. And you can do the same thing over here on the height side. If you double click on that. So For the height, it was also set at 0. I don't know why the automatic choosing, I feel like automatically usually does better than it did, but it didn't do very good on this one. So I also went into that one and changed it to 50 so that it would turn out prettier looking. Does that make sense?
So I had a similar problem where it was all clumped together, and I just stretched my graph wider. So I kept the same, the same 0, 10, 20, but I just extended it, and then it changed the shape. Does it matter if we change the axes or if we just stretch out our graph?
Not really. Like basically your goal is just to be able to tell that form, direction, and strength. So as long as you can tell that, you should try that and see what happens. Like you just made it bigger like that?
Yeah. And it spreads it out because then it puts farther distance between your markers.
Yeah, so you can see it less clumped together.
Yeah.
I see that. So yeah, as long as you can tell the form, direction, and strength, then that's all that really matters.
Okay.
And I mean, as far as the exam goes, you're not going to be able to paste a graph onto the exam. So you're looking at it to just look at it for you. So
okay, thanks.
Yeah. Okay, good question, Michelle. I think it was you that asked the question. So thanks for asking. Let me go back. Where is it? No. Okay, sorry, I'm gonna get it back. I have way too many things open on my computer. Oh, there it is, show all windows. And say Zoom's not wanting to let me go back to the right one that I want to go back to. Oh, there it is, okay. All right, so here's my graph. Looking for form, direction, and strength. So form, we're really kind of crossing our fingers that it's going to be linear because that's the only thing that we know what to do with in this class. So if it's not linear in this class, then we're just like pretty much out of luck. But looking at this one, it definitely does look linear. It would certainly pass the hot dog test, and it even doesn't even have to be that fat of a hot dog. It looks pretty good. Direction, positive. So as people's arm spans got longer, so did their height also got taller. And the strength, like I said, it's pretty strong. It's more of a skinny hot dog, and you don't even have to put the bun on it or anything else. It looks pretty good. So then the next step is to look at correlation. And in Excel, so in Excel, you can see that automatically once you put the data in, it already calculates correlation. It does the scatter plot. Like it kind of does everything for you just by pasting the data in there, which is kind of nice. Like the program that we used last semester, SPSS, which I'm sure you've seen a couple accidental references to in the textbook. There was a lot more steps to get to the answers that you wanted to find. So guess I'm telling you to like count your blessings. You guys are lucky that you have this easiness. There are a couple things that I don't like about Excel. Like it's a little bit harder to, it's not as flexible. You don't have as many options. Which I don't like as much, but it's probably like happy for you guys because you're like, I don't care about options. I just need to do what I need to do. So anyway, this is where that if we look at the model summary box right here, that's what I've got here on this page. And the model summary box will tell you what your correlation is, R. So R is your correlation, and this says it's 0.898. That's pretty close to +1. So again, that tells you that there's a pretty strong positive relationship between arm span and height, which is what we just saw when we looked at that scatter plot. So then the next step is to actually create our regression model. And again, here's the stuff that Excel will just automatically give you once you've pasted your data in. And where we want to look to get our model is over here in the coefficients table. So this column for B, those are going to tell you the values of our intercept and our slope. So using those, we can put together our model. So the top number, B0, is slope, and the bottom number, 0.707, the top number is intercept. The top number is intercept, the bottom number is slope. So strike what I said to begin with. Top number intercept, bottom number slope. So we end up with y hat is equal to 20.054 plus 0.707 times x. So kind of looking at the different pieces of the model for our intercept, what this number would mean was if we knew somebody who had an arm span of 0, then we would expect their height to be 20 inches. But, you know, obviously there's no one that has an arm span of 0. So as a number, doesn't really make sense, but as a piece of our model, it makes it work. So the really awesome part of our model, the one that we love, is the slope. So what the slope says is that for every 1 inch increase in arm span, we expect your, am I doing this right? Did I do, was arm span was x, right? So for every 1 inch increase in arm span, we expect your height to increase by 0.707. All right, so then we can use this model to make predictions. That's one of the reasons why we like to make regression models. So what would be the predicted height for a student whose arm span length is 65 inches? Well, we could just, one way to figure this out is we could just take 65, plug it in for x, solve for y hat, and that would give us our answer. But our amazing Excel spreadsheet will also do this calculation for us. So this is one of the few little blue boxes that we have on this Excel spreadsheet. The blue boxes are where you enter things yourself. And it's kind of down, here I'll back up to this one. You can see that, and this one doesn't have the 65 entered in, but you can see down here in this box, that's the box that I'm looking at here. So it's kind of at the bottom of your Excel window. And if you enter in any x value you want to, in this case we want to do 65, then it will tell us our predicted value out of that. All right, and some other things that this will also give us are some confidence intervals for the prediction. And there's 2 different intervals that it gives us for the prediction. So it's going to give us the confidence interval for the prediction. That's this first set here. And then it also gives us this thing called a prediction interval. So the difference between these depends on whether you're looking at a prediction for an individual or for a mean response. So the confidence interval is for a mean response. So what it would say is, on average, for all students whose arm span is 65 inches, then we would expect the average height for people with 65 inches arm span to be between 65.174 and 66.796. The prediction interval is for an individual. So this one says, okay, we have Sally, and Sally's arm span is 65 inches. What will we predict Sally's height to be? So that's what this prediction interval is. It says, okay, well, if Sally's arm span is 65 inches, then we would predict Sally's height would be between 61.866 and 70.10. So hopefully that kind of clarifies the difference between those two. All right, so of course, we can't do any kind of statistical methods without throwing in some tests of significance as well, some hypothesis tests. So we probably want to know, is arm span useful for predicting height? So if you couldn't tell from looking at the scatter plot, that was amazing, then we can also do this statistical test to figure out if arm span is useful for predicting height. And so one way to look at that is by doing a test on the slope. So the parameter for slope is beta 1. So the null hypothesis would be beta 1 equals 0, and the alternative hypothesis would be that beta 1 is not equal to 0. So we're basically saying slope is 0. So if slope is 0, then there'd be no relationship between the two variables, versus the alternative that slope is not equal to 0, meaning that there is a relationship between those two variables. And if we look back at that coefficients table there, then it will give us the test statistic and the p-value for doing this test. Is someone asking a question?
I was going to ask, what's the difference between the the beta, capital B and the smaller case B. It's in the
That's a
equation.
good question. So basically, it's the same as like the difference between X bar and mu. So X bar is from our sample, and mu would be the population value if we were to measure everybody in the population. So for regression, then B1 is the value that we calculate from our sample. That's how we get our model. But we're using that to estimate beta 1, which would be the value from the population. Like if we were able to measure everybody in the population and use that to create our model, then we would get beta 1, the actual value from the population. So kind of like p hat and p or s and sigma. So these are all the parameters, and these are statistics. So the statistics are the numbers that we actually calculate from our sample, whereas these parameters are the ones that we're trying to draw conclusions about because they're from our population. Okay, so back here at our test, the test statistic and p-value that we want to use for this come from this table here, and they're the ones on the bottom. So remember we said that that y-intercept, kind of not that interesting, like it's the ugly stepchild, okay? So except for getting the value to create your model, everything else you pretty much ignore in that table. So when you're looking for a test statistic and a p-value, it's always going to be about the slope. So this is the one that you want to take. So your test statistic would be that 9.778, and the p-value is essentially 0. It's got like, you know, it's a super duper small decimal value. That's what I'm looking for decimal. So if our p-value is really, really, really small, really, really close to 0, and we know when p is low, HO must go, then we're going to reject the null hypothesis and conclude that the alternative is true. So indeed, arm span is useful for predicting height, and the slope is greater than 0. Not surprising given what we saw in our scatter plot. All right, so now we have this model. We know that arm span is useful for making predictions for height. We know how to make predictions, and that's all fantastic. So now we want to know, okay, well, is the model good? Is it good at making predictions? And there's a couple ways that we measure whether or not the model is good. And the first way is R-squared. So R-squared measures the percent of the variation in the response that can be explained by the model. R-squared is actually just calculated by taking R and squaring it, but it measures something different than correlation. So once we've squared it, it measures something different. And in the end, it ends up being a number between 0 and 1, and we usually report that as a percentage, typically, although in your Excel spreadsheet, it's just in decimal form. So the key thing to remember, though, is that it's not the same as R. It does measure something different. And if you look in the model summary, so here's R, which we looked at earlier, and here's R-squared. So just thinking about, I think just put in connection in your mind, like the connection between the definition of R-squared, and put that with R-squared in your mind, and then you'll be okay. So if the problem asked, you know, what percent of the variation in height can be explained by arm span, well, you'd be like, oh, well, they're just asking for R-squared, so that's 0.806. And kind of one way to think about like R-squared is, I think if you think about the relationship between like height and weight. So does knowing somebody's height give you some information about how much they weigh? Well, yeah, it does. You know, usually, you know, really tall people are typically going to weigh more than really short people. But does everybody who is, say, 65 inches tall, do they all weigh exactly the same? Well, no, of course they don't. Well, why don't they weigh the same? Well, because there's more things than just height that influence how much you weigh. You know, you have genetics and gender and how much you eat and how much you exercise and you know, a whole bunch of other things that also go into how much you weigh. So if you want to kind of narrow it down, you could even think of it like, you know, breaking down like a pie chart, like how much of the pie or how much of the variation is because of height and how much is because of everything else. That's what this R-squared measured. It says, okay, you know, height accounts for this much, and, you know, everything else would be the leftover of that. So the higher your R-squared, the better that your model is at making predictions, because you're accounting for more of the variation. So in this one, height and our arm span and height that we looked at here, arm span is accounting for 80% of the variation that we saw in height. So that's actually pretty decent, meaning that we're actually going to get some not too bad predictions out of our model. So the closer you are to 100%, the better or more accurate your model is going to be at predicting.
Can R ever equal 1?
R can equal 1 if the relationship is perfect. So, you know, if knowing what X is tells you exactly what Y is.
Okay.
So in a scatter plot, for R to be equal to 1, like all the points would have to fall perfectly on a straight line.
Okay. Thanks.
Yeah, which doesn't happen in real life very often, but it'd sure be cool if it did. All right, the other thing that we look at when we're trying to figure out if our model's good, and especially to check the requirements in here, is the residuals. And the residuals are the leftover variation. And you can calculate a residual for each of the values in your data set by taking the observed Y minus the predicted Y. So Y minus Y hat. And a residual just tells you like how many units you were away from the predicted value. So if a residual equals 2.5, that means that the observed value was 2.5 units higher than the line, than what you would have predicted. And if the residual is negative 2.5, that means that the observed value was 2.5 units below the line, or below what you would have predicted or expected. And Excel, again, just by pasting that data in there, it's actually going to calculate all of the residuals for you. So here's the data, and then there's 2 columns right next to the data, one that has the explanatory variable, again, and the other one that shows the residuals there. And we basically use the residuals to help us check our requirements for regression inference. And these are the 5 requirements that we have for regression inference, and the ways that we're going to check those. So first requirement is that we have a linear relationship, and we can check that just by looking at our scatter plot. Did it look like it had a line? Did it have the hot dog shape? Another thing we can look at is the residual plot, okay? And I'll show you what that residual plot is in just a second. But we're looking there, we want there to be no pattern at all in the residual plot that would indicate that we do have a linear relationship. We want the error term to be normal. So to check that, we're going to do a QQ plot of the residuals. We want the variance to be constant. So again, that same residual plot that we talked about up here, we're going to look at that down here, and this time, again, we just want to see no pattern in the residuals, but specifically a megaphone pattern would indicate that we had a violation of the constant variance requirement. The X's are known constants, which we can't really check exactly, and then the observations are independent, and again, really just have to know how the data was collected. So if you're thinking about arm span and height, you know, these were students in my class. Does one person's arm span and height affect what somebody else's will be? No, right? I mean, if you look at your neighbor, you know, their height is not influenced by you. So, so those would be independent. So let me show you how to make those 2 plots. Whoops. So in Excel, we're going to take those residuals. Well, I think this is out of order. Sorry, here, let's go here. So I think what I just wanted to show here was that we're going to use these 2 columns here. And this is going to make the graph of the residual plot. Let's see, let me back up. I'm not being very clear. Okay, so this residual plot that we're talking about right here, that's the first graph that I'm going to show you how to make. And to do that, what you want to do is you want to highlight all of the data in both of these columns, the X variable and the residuals, because you're basically just making a scatter plot of the x and the residuals. So once you've highlighted that data, if you go to the insert menu and you choose charts, and then it'll allow you to choose scatter plot, then it will just make the graph for you. So this is the graph that I got when I did that. So what we're looking for here, what we want to see is random scatter. If we see random scatter, we're good. What would be some red flags are if we see a rainbow or a smiley face or a megaphone. So those things would indicate that one or more of those requirements are violated. So in this case, I don't see anything. Like, it just looks like a random scatter of points. I don't see any rainbows, no smiley faces, no megaphones. So this is good. Okay, the other graph that we're going to do is a QQ plot of the residuals. So that one's going to check this second requirement right here. So to do that, I just have to actually come in here and I'm going to copy all the residual values. So I just highlight them all and copy them. And then I pasted them into the other worksheet, the quantitative descriptive statistics. And I don't think I took a screenshot of that. And then you have to sort it. So you just make it a QQ plot with them just like you would with any other set of data in the quantitative descriptive statistics one. So here's what I got when I did all that. And I'm looking to see that the points fall pretty much on a straight line, or that there's kind of a random pattern going on with the points in the line. And they look pretty dang close to the line. A little bit of weirdness down here, but not too bad. I'd say overall they look like they fall on that straight line, so they're good. Okay, so taking all those things into consideration, here's the 3 plots again. So this is the original scatter plot. This one's the residual plot. And this one's the QQ plot of the residuals. Okay, and here's all of our requirements. So if we kind of look at all those 3 things together, it can help us. So linear relationship, we look at the scatter plot, yes, it looks linear. We look at the residual plot, we don't see any patterns, so check. Normal error term, well, we're gonna look at a QQ plot of the residuals, see that they fall mostly on a straight line, so we're gonna say check. Constant variance, we're gonna look back at this residual plot again. We wanna make sure there's no megaphone shape going on in there, which I don't see, so check. And then these other 2, you know, like I said, it can't be checked directly, so we'll call those goods. So we would say, yes, we meet the requirements, our results are, you know, valid, and we can draw these conclusions and be happy, I guess, or, you know, ta-da, we finished our analysis. It's kind of a lot for regression, huh? Big problems. Okay, so that's it. We made it to the end of regression and of all the new material that we have for the exam. So does anybody have any questions or anything that you want me to go back over or anything?
So will we still get to use 1 page of notes and our flow charts?
Yes. Yep, you can still have all those.
Thank you.
On the assignment, what's it called? The group quiz that we did yesterday.
Uh-huh.
Number 8 and 9, I don't know what I did wrong.
I can pull those up and look at it for you.
Yeah, that'd be cool.
Okay, hang on.